Thank you very much for the introduction, and thank you for inviting me. I'm Irene D'Amico. I'm from the University of York. There's a big light up there, and I will be telling you about using density functional theory for quantum thermodynamics purposes. This should work any minute now. The first thing I will try to tell you is why I suggest that density functional theory could be useful. And the second thing, I'm not assuming that people here know about density functional theory, so I will do a very, very brief crash course on some concept of density functional theory that I wish you to know in order to understand what will be the results and the message I try to convey through the talk. Then I will talk about results, how to quantify quantities we are interested in from quantum thermodynamics using thermal DFT. And I will then show a case study and some new results calculated with density functional theory. So why density functional theory? Well, if we consider systems that are, a few qubits, idealized system, maybe no particle interaction, maybe systems that are analytically solvable exactly, we all know how to solve them, and this is very easy. However, also in the context of the quantum energy initiative, in which we want to look at something a bit bigger and a bit more complicated, if we actually look at realistic systems with many qubits where we have particle-particle interaction, maybe we're interested in real material, and we would like also to measure experimentally quantities that are non-local or non-observable in the sense that they are not represented in quantum mechanics by an observable. And maybe we want to do some calculation of energy in the case of complicated system. Then we are often in trouble. So that is, I think, where density functional theory can be of help. So in writing many-body quantities like entanglement, like work, quantum work, like energy, as an expression of local quantities, so local quantities that then could also be measured as local operators, or providing, in certain cases, good approximation for other quantities, and for example, many-body wave function. Give expression, as I said, of quantities that are non-observable, like work, or non-local, in terms of properties that are measurable in experiments. And in general, again, I underline that density functional theory is probably the theory most used in order to calculate energies of complex many-body systems. Density functional theory was derived initially by Onenberg and Kohn, and then, by Onenberg and Kohn for the ground state, for ground state systems. Then many various extensions were demonstrated during the year, so extension to spin-dependent systems, extensions to time-dependent systems, especially with focus on the adiabatic regime that also allowed to calculate excited state or properties of excited states, more than excited states. There are extensions to lattice Hamiltonian, both spin chain type of Hamiltonian like the XXZ, but also fermionic lattice Hamiltonian like the Hubbard Hamiltonian, for example. There are extensions to thermal systems and to ensembles, so systems of described by mixed states, for example. And both of these are more in their infancy with respect to the other flavors of density functional theory. Mainly, density functional theory have been used to calculate equilibrium property, for example, ground state energy, band structure calculations, properties of nanostructure, like optical properties of nanostructure, magnetic properties of material. It has been used to study graphene, and so on and so forth. There are well-established public codes for calculating this type of properties. And the nice thing, again, is that with density functional theory, at least with the part of density functional theory that is well established, there is a possibility of working with the calculating properties of really big systems. I cite here these two papers which have actually calculating properties for systems with millions of atoms. So I'm talking, you know, people have done this. I'm not claiming that this is possible immediately with quantum thermodynamics, but for the type of flavors of density functional theory that are well established, indeed, you can do calculation for very large and complicated systems. And so in relation to quantum thermodynamics, you know, time-dependent density functional theory, lattice-Hamiltonian density functional theory, thermal density functional theory, and probably ensemble density functional theory could be of interest. Also, this is my opinion. So, in a very, very high level kind of, not even a crash course, information about, basic information about density functional theory, I just want to point out that all these different flavors of density functional theory are based on two things. One is a Nonenberg-Kohn-like theorem. For time-dependent density functional theory will be the Runge-Kutta theorem. For thermal DFT will be the Mermin theorem. And on a set of Kohn-Sham equations. I will come back to this, but keep in mind these two ingredients are there for all the flavors of density functional theory. And then if you want more information on the different flavors, here I give some references, some of my favorite references. This is, for example, about model Hamiltonians, so lattice Hamiltonians. But in general, you can Google density functional theory, and you can find books and reviews as much as you like. So, first ingredient, the Nonenberg-Kohn theorem. I will just here really cite it for the case of the ground state. Again, that's where everything started with density functional theory. We start with an Hamiltonian. The idea is that we have an Hamiltonian with a kinetic term and an external kinetic term, and an external potential, and a two-body interaction term, so particle-particle interaction. And then what the theorem demonstrates is that we have a one-to-one correspondence. So given one, you can derive the other, or if you like, one contains the same information as the other, between the ground state local density, NGS, which is a function of three variables, the external potential, so this object here, and the many-body ground state, the full-fledged many-body ground state, which is a function of 3n and the number of particle variables. This is the definition of the local density. So the key message here is that the many-body ground state, this very complicated object, can be actually described completely in terms of the ground state local density. It is indeed the functional of the ground state local density. So if I know how to do that, in general, I can calculate this, and from this, I can calculate any property that is expressed in terms of the ground state. Which means, in particular, that if I have observables, so mean value of a certain operator over, in this case, I'm talking about ground state theory, so in this case, over the ground state, which are in general a functional of the many-body ground state, I can actually rewrite them as a functional of a much simpler object, that is the ground state local density. So this is an existence theorem, which means I know I can do this. It doesn't tell me the form of the functional. And this is, of course, one of the issues in density functional theory, but I will go through that, at least for quantum thermodynamics and what we have done. But keep this in mind. We are transforming a functional of a very complicated object into another functional of a much simpler object. This is the beauty of density functional theory. The next bit is, given that I know this functional, how do I calculate the local density? Because that, if I have to solve the many-body Schrödinger equation, I'm back to square one. Well, the way we do this is to use the Kohn-Sham system, or if you like, the Kohn-Sham scheme. So, Kohn and Sham have demonstrated that if I take a many-body interacting system, full interacting system, which I would have to solve using my many-body Schrödinger equation in order to calculate the properties, I can put this system in correspondence with a specific non-interacting system that is known as the Kohn-Sham system, which has the property of having exactly the same ground state density. I'm now talking about ground state, but again, this can be extended then to different flavors of DFT as the interacting system. So the way to calculate the main ingredient for many-body systems, so the density, the local density, is to solve the Kohn-Sham system, which is now a set of equations of single particle equation, much simpler. From there, calculate the density. From the density, calculate all the properties of the many-body system as functional of this density. There is always a price to pay. The price in this case is that the Kohn-Sham system has an Hamiltonian which includes what is known as the exchange correlation potential, that is known to be a functional of the density. However, it's an unknown functional. By now, in all the various flavors of DFT, there are many approximations for this functional, which are useful in various circumstances, at least for the flavors of DFT that are best developed. So I will be talking about two different types of functionals in this talk. The first is what I just talked about, the exchange correlation potential. I needed to solve the Kohn-Sham equation and find the local density of the system. And second, are functional that are like, for example, the mean value of an operator, are functional that have a dependence on the local density of the quantity of interest. Okay, one warning is that while DFT promises you to give you the exact many-body local density and observables given that you know the functional, it doesn't give you any promise about the wave function. So if you don't have the functional of the wave function, you cannot blindly take the Kohn-Sham wave function and say this is the function of my many-body system. Said that, the wave function of the Kohn-Sham system often is a very good approximation to the wave function, but just to mention is not a promise. Here I'm interested in quantum thermodynamic protocols. So let's say we want to produce work. We are at a finite temperature in the canonical ensemble. We start from a many-body system in a thermal equilibrium. And then we detach the system from the bath. We drive our system as a closed system. I will be discussing closed system. So we have a unitary dynamics with production of work. And we finish in a state that is out of equilibrium. If I now want to go back to some thermal equilibrium state, I would have to connect again my system to the bath. And then with an irreversible process, so dissipation of heat, I will recover my equilibrium state. From the point of view of from the point of view of many-body physics, this is a very complicated dynamics. And so the idea is to use concepts and develop the theory of density functional theory in order to solve this type of problem. So we start with a lot of question marks. So, okay, how do I have functional for thermal DFT? The thermal DFT is not very much developed. VXE approximation similar, we don't have much. If we want to drive it, we have to go to thermal time-dependent density functional theorem, theory. Do we even have the fundamental theorems for this? I want projective measurements to calculate the work. How do I represent this within density functional theory? Which are the densities that are important for this? I have a reversibility, dissipation again. what does it mean write, for example, the entropy related to the dissipation in terms of densities? How do I write the functional, which densities, and so on and so forth. So I'm doing, of course, with out of equilibrium and mixed state. Should I use ensemble DFT? Lots of questions. This is indeed uncharted territory. So we have to look and demonstrate, first of all, that the quantum thermodynamic properties of interest are indeed functional of the local density. We would have to understand of which local densities, find explicit expression for the functional that are also workable approximation, because I may have an expression, but I cannot actually calculate it easily, and that's a problem. And then we want to benchmark the approximation with exact results and find your results. So what I will be telling you about in the next part of the talk is our progress in this direction. The work I will be presenting is a work that has been recently published. It's in collaboration with Antonio Palamara, that is a bit the star of this work. Here he is. Francesco Plastina, that is in the audience up there, and Antonello Sindona. And we have derived, as you can read, quantum thermodynamic properties via thermal density functional theory in the case of closed quantum systems. So we want to show that the quantum thermodynamic properties of interest can be actually written as functional, demonstrate, first of all, that they are functionals of thermal equilibrium densities. And then we went to find workable expression. And then, as I said, benchmark on test system and calculate some new results. First of all, we have to adapt the Mermin-Cohn theorem to the case of a closed quantum system and on a lattice. And so we work on a lattice because this is usually the frame in which we describe qubits. So we were interested in working in a lattice. Our Hamiltonian is an Hamiltonian with a kinetic term and a many-body term, and an external potential, which is a function of some external parameters and some big AI local operators. So this is our Hamiltonian. Can be the Hamiltonian of fermions, can be the Hamiltonian of bosons, can be the Hamiltonian of a spin chain. We have corresponding Gibbs states written in the usual way, and we can define equilibrium density, generalized equilibrium densities in this way. These are the thermal average of our local operator. If our local operator is the occupation operator on a site, this becomes indeed the local occupation on site I. But it can be in principle a different operator. And what the theorem demonstrates is that the set of parameter lambda I uniquely, given a set of parameter delta I, lambda I, this uniquely define the set of local densities, small a, I, beta, and this uniquely define the thermal state, the equilibrium thermal state of the system. So these are one-to-one correspondence, which tells us that indeed these local densities, or if you like, this generalized equilibrium density, become the fundamental descriptors of my many-body system. I can use them to describe the properties of my many-body system. So I will just now go through some results. So first of all, the Helmholtz free energy. This is again our Hamiltonian. In general, the free energy of our system is given by this expression, which is minimized at equilibrium. If I look at this expression and I think about equilibrium, it's clear that this would become the rho at equilibrium. Because of the previous theorem, I know that I have this one-to-one correspondence. And so automatically at equilibrium, my free energy becomes a functional of my local densities. In particular, if I now consider the form of the Hamiltonian, I have that I will have a universal functional, which just depends on the form of H naught, so on the form, for example, of the many-body interaction. And then a part of this functional that explicitly depend on the parameters lambda I in this form. What is interesting is that now, if I consider the Hellman-Feynman theorem, I can see that the derivative of the free energy with respect to the parameter delta E is nothing but my local generalized density. So this is a way to calculate, this is indeed the way we will use in the Consham scheme to calculate the local densities. Work and the distribution, the probability distribution of work is not an observable. Nothing tells us that we can actually write it in terms as a functional of our local density. But if we look at it and we write it, we consider the characteristic function of the work, which is the Fourier transform of the work as written here, and from which I can derive all the moments of the work distribution in this way, then in the case of a sudden quench, I can see that I can indeed write the characteristic function as a thermal average here. Because it's a thermal average and this object is a functional of my local initial local densities, then I have that my characteristic function, indeed, even if it's not an observable, is a functional of my densities, my local densities. And so I can do the same for any moment of the work distribution, which also become then explicitly functional of my local density with the with initial local density with the parametric dependence on the working parameter, initial and final working parameter. That's nice, we know they are functional. And this tells us that we can calculate now PW through thermal DFT as long as we can express this functional in a meaningful way. So we have done this for the case of the first and second moment of the work distribution. In a sudden quench, we have that the first moment is nothing but this. So it's very simple. This is the average work. And the second moment can be written in this way. We have two contributions. The first contribution, here it is, correspond to the contribution we have in the case in which the initial and final Hamiltonian, so the beginning and at the end of the quench, commute. And this is the explicit term for it, the explicit form for it that we can use. The second term is the term that is occurring because in the case in which the initial and final Hamiltonian don't commute, we give an explicit way of, oh my God, okay. Okay. I will really rush. You can look at the paper to have an expression for this, okay. Interestingly, we are able to calculate, to demonstrate that also the irreversible entropy is a functional of the initial equilibrium densities. Initial and final in this case, it depends on both, okay? And we have, in the case of infinitesimal sudden quench, also an explicit expression for it. And this is an irreversible process. It was absolutely not a given that you could have this as a functional of your densities. So we want to benchmark the results somewhat that we have. We use an homogeneous 1D fermionic Hubbard model used for many cases, especially in the case of strongly correlated systems. And it's not an easy system. If you have 6 sites, you have more than 4,000 states. If you have 10 sites, you have more than 1 million states. If you're not convinced, this is the low and the midsection of the instantaneous spectrum of a 6-site Hubbard model chain, non-homogeneous with increasing many-body interaction, so it's a complicated system. We consider upfilling, and this system has phase transitions. The most famous is the metal-to-mott insulator transition. We consider repulsive fermions. And also, if we drive the system in this way, so from a quasi-homogeneous potential to a zigzag potential, we can also have a transition to a band insulator system. And when we solve this system with our Consham equation and find the density and compare the exact result here, exact result for this is a dimer for the extracted work and the irreversible entropy. This is the Mott insulator phase, no work extracted. The band insulator phase, most work extracted. This is the metallic phase in between. Metallic phase that is very well described and pointed out by the reversible entropy. We see that with thermal DFT, we basically obtain results that are basically indistinguishable. And the functional for exchange correlation was not particularly good. So we check with larger chains, the densities are well reproduced, the local density. The extracted average work is very well reproduced. This is the extracted average work with respect to interaction for different values of my local potential. And these are new results. Well, new results in the sense that are derived using thermal DFT. This is with a linear potential. So we are doing a sudden quench for the potential that goes from this to this. And here we are using a sudden quench with the potential harmonic that goes from here to there. And again, you can see that in the Mott insulator phase, we have a least extracted work in the case of a linear potential. While in the harmonic potential, we have the biggest extractive work in the case of the Mott insulator phase. If I would have done the opposite, so not this, from here to here, but from here to here, type of variation of the potential for the harmonic potential, I could have not extracted work, okay? Importantly, this is 16, this is 20 sites. These are not calculated, you cannot calculate them analytically. We are really at the limit and after the limit for calculating analytically. So exactly, not analytically, pardon me, it's always numeric, but exactly solving the system. So this you can obtain only, well, in this case with DFT, with some not exact, you have to use a method that is not direct diagonalization. Okay, I'm rushing. These are my collaborators. These are the three collaborators of the direct collaborator of this, to this work. These are other collaborators with who I worked on this, on matching density functional theory with quantum thermodynamics on work, which I didn't have time to talk about. And these are the conclusions. So these are the other works in which I use density functional theory for finite time dynamics to the aims of quantum thermodynamics. This we put in correspondence the entanglement and average work in the case of the superconductive insulator transition. And this is the work that I have presented today. And that's it. So thank you very much for your attention.
Thank you, Irene. Are there questions?
Thanks for the great talk. Oh, sorry. Okay. Sorry. That was really great. I don't know much about DFT, but I heard a lot about it. And I think I finally understood some things today. So I wanted to say, okay, so I understand that even with this new approach, thermal DFT, we get the thermal equilibrium local densities, right? Am I correct when I say local densities for the many body states?
That is correct, yeah.
But nevertheless, then at some point you talked about the second moment, and I guess that goes towards the direction of calculating two-point correlation functions, such as, and you can still do it.
Yep, that's
fantastic.
Thing. That's a nice thing. So, indeed, that was the message. Even if we didn't know at the beginning, so we, you know, so even in that case, we can express the moments. We are talking about a sudden quench here in terms of the local density, and that in the case of the work is just the initial local density, equilibrium density, okay, equilibrium. In the case of the irreversible entropy, it is a functional of both the initial and final equilibrium densities.
Okay. Thank you so much.
Yeah.
Yeah, but maybe just to follow up on this. So the 2-point correlations, it's in time or in space? I thought it was in time, but when you calculate the moments of the work, it's
in time. I mean, the point is you measure the work at the beginning and at the end. Yeah.
Yes, but it's okay. But then because never mind. Maybe I can ask later. I just had 2 small questions.
Yeah.
Do you have any conditions on the operator's AI in the model? Do they have to commute or?
No, they are local operators.
Okay.
In the case in which, okay, let me go back to the Hamiltonian. There are some pathological cases in density functional theory in which you cannot do the mapping with the conscious system, but usually are pathological cases.
Okay.
In the case of the theorem, if I remember correctly, I can't see. That's a funny one. It doesn't arrive on my screen. That's the point. Yeah, I'm trying. Ah, here it is. That's great. Okay. In the case of... so in the case in which... in the case in which these lambda are all the same for any site, then you have to have that the sum of the operator, so the sum over I of AI, so with lambda I all the same, have to I think, non-commute, if I remember correctly, with H naught. That's a condition, but for the rest, no, it's quite general.
Okay, so it's kind of a generalized Legendre transform, then this duality, maybe?
Yeah, you can look at it probably, yeah.
Okay.
So this is a way of expressing the theorem of theorems of density functional theory, and in this case, as I said, these are local operators, and they don't have to be the local, it's a local operator, that doesn't have to be the local density operator. Yeah. So this is much more general. Yeah.
Okay.
Thanks a lot.
Thank you very much.